Picture this. It's 14:10 in Prague, and the only way to tell time is by watching shadows creep across sundials or listening for church bells that ring whenever the monks feel like it. No smartphones, no watches, not even a decent hourglass that doesn't break every other week. Then suddenly, someone decides to build a machine so complex and ambitious that it makes modern smartwatches look like children's toys. We're talking about creating the world's most sophisticated timekeeper, using nothing but hammers, files, and medieval engineering genius. The Prague Astronomical Clock wasn't just about telling time. This mechanical marvel was designed to track the sun's position through the zodiac, show moon phases, display saints' days, and even predict eclipses, all while making little wooden figures dance on the hour. It's like someone in the 1400s decided to build the internet, except instead of cat videos, it displayed the entire cosmos on a single dial face. But here's what really blows my mind about this whole project. Master Hanuš and his team of clockmakers had to invent half the techniques they needed as they went along. There were no instruction manuals, no YouTube tutorials, and definitely no customer service hotline. When they needed a gear with exactly 120 teeth to make the moon phase display work correctly, they had to figure out how to cut each tooth by hand with mathematical precision that would make modern engineers sweat. The workshop where this miracle happened was probably smaller than your garage, filled with the constant sound of hammering metal and the smell of coal smoke from the forge. 3 men working by candlelight and whatever sunlight managed to creep through small windows, creating something that would keep accurate time for the next 6 centuries. Talk about job pressure. Mess up one calculation, and the entire city would be late for everything until someone figured out how to fix your mistake. What makes this story even more incredible is the sheer ambition of what they were attempting. Most clocks of that era were simple affairs that maybe rang a bell once an hour if you were lucky. But Master Hanuš and his crew decided to build something that would display not just hours and minutes, but the complex dance of celestial bodies across the heavens. They were essentially building a computer out of brass gears and iron wheels, programmed to run astronomical calculations automatically for centuries. The first challenge they faced was creating what clockmakers call the going train. This is the heart of any mechanical clock, the series of gears that transforms the steady pull of a falling weight into the regular tick-tock rhythm we associate with timekeeping. Sounds simple enough, right? Wrong. Every single component had to be forged by hand from raw iron and brass, shaped with files and chisels until it was precise enough to mesh perfectly with its neighboring parts. Starting with the great wheel, the largest gear in the entire mechanism, Master Hanuš would have begun by heating iron in his forge until it glowed orange hot. The wheel itself needed to be perfectly round, with exactly the right number of teeth spaced at mathematically precise intervals. One tooth too many or too few, and the entire clock would run fast or slow, making it useless for a city that needed accurate timekeeping. The process of cutting each individual tooth was painstakingly slow, requiring steady hands and an eye for detail that would shame a surgeon. But the great wheel was just the beginning. Next came the center wheel, which had to mesh perfectly with the great wheel, while also driving the next gear in the sequence. Then the third wheel, the fourth wheel, and finally the escape wheel, each one smaller than the last, but requiring the same obsessive attention to detail. The mathematical relationships between these wheels determined everything about how the clock would function. Get the ratios wrong, and you'd have a very expensive collection of scrap metal instead of a timepiece. The escape wheel deserves special mention because it's probably the most crucial component in the entire mechanism. This gear works with something called a verge and foliot escapement, which sounds like medieval gibberish but is actually pure mechanical genius. The escape wheel has specially shaped teeth that catch and release a vertical rod called the verge, which rocks back and forth like a metronome. This rocking motion is what creates the familiar tick-tock sound of mechanical clocks. Attached to the top of the verge is the foliot, an iron crossbar with adjustable weights that can slide back and forth. Here's where things get really clever. By moving these weights outward, you make the foliot swing more slowly, which makes the entire clock run slower. Move them inward, and the clock speeds up. It's like having a volume control for time itself. Master Hanuš would have spent weeks adjusting these weights, testing the clock's accuracy against sundials and water clocks until he achieved the precision needed for public timekeeping. The physics behind all this is actually pretty fascinating when you think about it. The falling stone weight provides a constant downward force, trying to make all the gears spin as fast as possible. But the escapement acts like a mechanical brake, allowing the gears to advance only one tooth at a time, at regular intervals. It's a constant battle between gravity trying to speed things up and the escapement holding it back, creating the steady rhythm that divides time into measurable units. Testing this going train was probably the most nerve-wracking part of the entire project. Picture Master Hanuš and his assistants gathered around their workbench, watching as they slowly released the weight for the first time. Would the gears mesh properly, or would something bind up and jam the whole mechanism? Would the escapement regulate the motion correctly, or would the clock run wildly fast or stop entirely? The first successful test run must have felt like watching your child take their first steps, except your child was made of iron and brass and would hopefully keep walking steadily for the next several centuries. Once they had the basic timekeeping mechanism working reliably, the real complexity began. Because this wasn't just going to be a simple clock that told hours and minutes. The Prague Astronomical Clock was designed to display the apparent motion of the sun through the zodiac, track lunar phases, show the positions of known planets, and indicate various feast days and holy periods throughout the year. Each of these additional functions required its own set of gears, carefully calculated to rotate at exactly the right speed relative to the main timekeeping train. The dial work alone was a masterpiece of medieval engineering. The main face needed to accommodate a 24-hour ring, because medieval timekeeping divided the day differently than our modern system. There was also the zodiacal ecliptic, a ring showing the 12 astrological signs that the sun appears to move through during the course of a year. Getting these rings to rotate at the correct speeds relative to each other required gear ratios that would challenge modern engineers with calculators and computers. The sun and moon indicators were particularly tricky because they needed to move independently while still being synchronized with the main timekeeping mechanism. This meant creating reduction gears, smaller gear trains that stepped down the rotation speed to match the astronomical periods being displayed. The moon indicator was especially complex because it needed to show not just the moon's position relative to the sun, but also its phases throughout the month. The lunation display was perhaps the most ingenious feature of the entire clock. Master Hanuš created what was essentially a simple computer program made of metal, using a shuttered sphere that revealed varying amounts of a painted moon face as it rotated. Half the sphere was painted bright silver to represent the illuminated portion of the moon, while the other half remained dark. As the sphere slowly rotated once per month, viewers could see the moon appear to wax and wane just like the real moon in the sky. But even with all these astronomical complications, Master Hanuš wasn't finished. The clock also needed to strike the hours, which meant building an entirely separate mechanism called the striking train. This system used something called a count wheel, a gear with notches cut around its edge that determined how many times the bell would ring for each hour. At the appropriate moment, lifting pins would release a hammer to strike the bell, with the count wheel ensuring that 1 o'clock got 1 strike, 2 o'clock got 2 strikes, and so on. As if that wasn't enough mechanical complexity for one project, the Prague clock was also designed to include automata, small figures that would move when the striking sequence completed. These little wooden people weren't just decorative afterthoughts. They served an important function in medieval society by providing visual confirmation that the clock was working properly. In an age when most people couldn't read numbers, seeing the figures move, was proof that the great machine was still faithfully keeping time. The automata were powered by their own separate mechanism, a pinned barrel system that used carefully placed pegs to operate levers at precisely the right moments. Picture a player piano, except instead of making music, it was making wooden saints nod their heads and carved roosters flap their wings. The timing had to be perfect, synchronized with the striking train so that the figures would perform their mechanical dance just as the bells finished ringing the hour. Creating all these interlocking systems required not just technical skill, but also an understanding of astronomy, mathematics, and mechanical engineering that was centuries ahead of its time. Master Hanuš and his assistants were essentially building an analog computer designed to run complex calculations automatically, using nothing but the tools and materials available in medieval Prague. The amount of planning required for such a project boggles the mind. Every gear ratio had to be calculated in advance. Every bearing surface had to be precisely positioned, and every moving part had to be designed to work harmoniously with dozens of other components. One small error in the early stages could cascade through the entire mechanism, making the final product useless. It was like building a house of cards, except the cards were made of metal and needed to keep standing for centuries while constantly moving. The workshop atmosphere during those crucial months must have been electric with tension and excitement. Imagine the pressure of knowing that the entire city of Prague was watching your progress, waiting to see if this ambitious mechanical marvel would actually work. Every day brought new challenges that had never been solved before, problems that couldn't be looked up in any book because no one had ever attempted anything quite this complex. The precision required for each component would make modern machinists weep with frustration. Take the pinion gears, for example. These small gears with just a handful of teeth had to mesh perfectly with much larger wheels, transferring power smoothly without binding or slipping. Master Hanuš had to forge each pinion from solid iron, then file every single tooth by hand until it was exactly the right shape and size. We're talking about tolerances measured in fractions of millimeters, achieved using nothing but skilled hands and keen eyesight. The lantern pinions were particularly challenging pieces to create. Picture a tiny cylindrical cage made of iron bars, with each bar serving as a gear tooth. The spacing between these bars had to be mathematically perfect, or the pinion would jam against its mating wheel, like trying to force a square peg into a round hole. Each bar was individually forged, shaped, and fitted into the pinion frame with obsessive attention to detail that would drive most modern workers to early retirement. But here's what really gets me about this whole project. While Master Hanuš was solving these mechanical puzzles, he also had to worry about the metallurgy of his materials. Iron in the 1400s wasn't the consistent, predictable steel we use today. Every batch of metal had slightly different properties, different carbon content, different impurities that could make a gear tooth crack under stress or cause a bearing to wear out prematurely. The clockmakers had to become experts not just in mechanical engineering, but also in the mysterious art of metalworking. The process of truing each wheel was like performing surgery with a hammer. After forging a gear blank, Master Hanuš would mount it on a primitive lathe powered by an apprentice turning a hand crank. Then came the delicate work of filing and adjusting until the wheel was perfectly round and balanced. One heavy spot could throw off the entire mechanism's timing, making the clock gain or lose precious minutes throughout the day. The master would spin each wheel repeatedly, feeling for the slightest wobble or vibration that might indicate an imperfection. Testing the completed going train must have been both thrilling and terrifying. Picture the scene: 3 grown men hovering over a wooden test stand, watching as gears turned for the first time. The great wheel slowly rotating, driven by a cord wrapped around its rim, with a stone weight hanging from the other end. Each gear in the train stepping down the rotation speed, transforming the steady pull of gravity into the rapid oscillation of the escapement. The sound would have been the first clue to success or failure. A properly running gear train has its own musical quality. A smooth whirring punctuated by the regular tick of the escapement. But if something was wrong, the workshop would fill with grinding, scraping noises that meant hours or days of additional work to fix whatever wasn't meshing properly. The apprentices probably learned to read their master's mood by listening to the sounds coming from the test stand. Getting the escapement to work consistently was probably the most maddening part of the entire process. The verge had to be positioned at exactly the right angle relative to the escape wheel, with just enough clearance to allow smooth operation without being so loose that timing became erratic. Too tight, and the mechanism would bind up completely. Too loose, and the clock would run wildly fast, gaining hours instead of keeping accurate time. The foliot weights became Master Hanush's fine-tuning controls, but adjusting them was more art than science. Moving a weight outward by just a few millimeters could slow the clock by several minutes per day. Finding the perfect position required endless patience and careful observation, comparing the clock's performance against sundials and other time references available in medieval Prague. It was like tuning a musical instrument, except the instrument was made of iron, and the song it played was the passage of time itself. Once the basic timekeeping mechanism was running reliably, the real complexity began with the astronomical displays. The ecliptic ring alone required mathematical calculations that would challenge modern astronomers. This ring had to rotate once per year, showing the sun's apparent path through the zodiac constellations. But since the medieval year was slightly different from our modern calendar, Master Hanuš had to account for leap years and other calendar irregularities that wouldn't be fully understood for centuries. The gear ratios needed for astronomical accuracy were mind-bending in their precision. To make the zodiac ring complete one revolution per year, while the hour hand completed 365 revolutions, required a reduction ratio of exactly 365 to 1. Achieving this with medieval gears meant creating complex gear trains with multiple stages of reduction, each stage introducing potential sources of error that could accumulate over time. The moon phase display pushed the boundaries of mechanical ingenuity even further. Master Hanuš needed to create a mechanism that would complete one full cycle every 29.5 days, matching the lunar month with astronomical precision. This fractional timing was incredibly difficult to achieve with simple gears, requiring clever combinations of wheels and pinions that could approximate the moon's irregular orbit. The shuttered moon sphere was pure mechanical poetry. Imagine a hollow ball, half painted silver and half left dark, rotating slowly inside a circular opening. As it turned, viewers would see varying amounts of the bright half, creating the illusion of waxing and crescent moons. The timing mechanism had to be precise enough that the displayed moon phase would match the real moon in the sky, month after month, year after year. But the astronomical complications were just part of the challenge. The striking train added another layer of mechanical complexity that had to work in perfect harmony with the timekeeping mechanism. The count wheel system was like an early form of programming, using physical notches to store information about how many times the bell should ring for each hour. The lifting pins that triggered each bell strike had to be positioned with clockwork precision. Too early, and the bell would ring before the hour was complete. Too late, and people would start wondering if the great clock had finally broken down. The mechanism needed to remember what hour it was and automatically select the correct number of strikes, all without any electronic controls or computer logic. The automata added yet another dimension of complexity that modern engineers would probably solve with electric motors and computer control. But Master Hanuš had to create mechanical life using nothing but springs, levers, and carefully timed gear trains. Each figure's movement had to be choreographed to match the striking sequence, creating a mechanical theatre performance that played out precisely on schedule, hour after hour, day after day. The pinned barrel that powered the automata was like a three-dimensional music box with pegs arranged in specific patterns to operate different levers at exactly the right moments. Programming this mechanical computer meant calculating not just when each figure should move, but also how long each movement should last, and how much force would be needed to operate the linkages and pulleys that brought the wooden figures to life. Synchronizing all these separate mechanisms was perhaps the most challenging aspect of the entire project. The going train, the astronomical displays, the striking train, and the automata all had to work together like musicians in an orchestra, each playing their part at precisely the right tempo. One mechanism running slightly fast or slow would gradually throw the entire system out of sync, making the clock unreliable for public timekeeping. The mathematical relationships between all these moving parts had to be calculated with slide rule precision, using nothing but medieval arithmetic. Master Hanuš was essentially solving differential equations in his head, working out gear ratios that would remain accurate for centuries of continuous operation. One small error in these calculations would compound over time, eventually making the astronomical displays worthless for their intended purpose of tracking celestial events. The installation phase brought an entirely new set of challenges that would test every aspect of Master Hanuš's engineering skills. Moving a delicate clockwork mechanism from the safety of a workshop into a stone tower was like performing surgery during an earthquake. Every gear, every wheel, every precisely calibrated component had to survive the journey and then be reassembled in a space that definitely wasn't designed with mechanical clocks in mind. Picture the scene as the clockmakers approached the tower with their precious cargo. Each major component was wrapped in cloth and packed into wooden crates like fragile treasure. The great wheel alone probably weighed more than 2 grown men, and dropping it would mean starting over from scratch after months of careful work. The apprentices must have been sweating bullets as they carried these irreplaceable pieces up narrow stone stairs that were probably built more for defense than for moving delicate machinery. The tower itself presented problems that no workshop test could have anticipated. Medieval stone walls weren't exactly known for their precision engineering. Finding level surfaces to mount the clock frame was like trying to build furniture in a cave. Master Hanuš had to work with what he found, using wooden shims and iron wedges to create the stable, perfectly aligned mounting points that his mechanism demanded. Seating the main frame on wall irons was probably the most nerve-wracking moment of the entire installation. These iron brackets had to support not just the weight of the mechanism itself, but also the dynamic forces created by all those moving gears and oscillating escapements. One weak mounting point could bring the entire project crashing down, literally destroying months of careful work in a single catastrophic failure. The weight system posed its own unique challenges. The driving weights needed to hang freely down a shaft that extended deep into the tower, providing enough drop to keep the clock running for days between windings. But medieval towers weren't built with clock weights in mind. The masons had to modify existing stonework, carefully cutting channels and installing guide systems to ensure the weights could fall smoothly without jamming against irregularities in the walls. Hanging those massive stone weights for the first time must have been terrifying. Imagine slowly lowering several hundred pounds of stone down a narrow shaft, knowing that if the rope broke or the pulley system failed, someone below was going to have a very bad day. The weights themselves had to be precisely calculated, not just for their driving force, but also for their size and shape to fit within the confines of the tower structure. Aligning the motion work to the facade was where theory met brutal reality. All those carefully calculated gear ratios and precisely positioned displays meant nothing if the hands couldn't reach the dial face properly, or if the astronomical rings didn't align with their intended positions. Master Hanuš probably spent days making tiny adjustments, filing metal here and there, adjusting mounting positions by fractions of inches to get everything lined up correctly. The dial face itself was a masterpiece of medieval craftsmanship that had to integrate seamlessly with the mechanical components behind it. The 24-hour ring needed to be positioned so the hour hand would point to the correct numbers throughout its rotation. The zodiacal ecliptic required even more precision, since astronomical accuracy depended on perfect alignment between the mechanical calculations and the visual display. Getting the astronomical displays to show the correct information required synchronizing the mechanism with actual celestial observations. This wasn't just a matter of setting the time. Master Hanuš had to align his mechanical cosmos with the real universe outside. The sun indicator needed to point to the correct zodiacal sign for the current date, while the moon display had to match the actual phase visible in the night sky. The commissioning process was where all the theoretical knowledge met practical reality. Setting noon by a gnomon mark sounds simple enough. But remember that medieval Prague didn't have standardized time zones or atomic clocks for reference. The shadow cast by a sundial was probably the most accurate time reference available, but shadows don't work on cloudy days or during the winter months when the sun barely clears the horizon. Master Hanuš had to become an amateur astronomer, observing the sun's position at its daily peak and adjusting his mechanical sun to match. This process probably took weeks of careful observation and adjustment, waiting for clear days when accurate solar observations were possible. Every small error in this initial setup would propagate through all the astronomical displays, making them gradually less accurate over time. The foliot masses became the fine-tuning controls that could make or break the entire project's success. These sliding weights were like the volume knobs on a medieval radio, except instead of controlling sound, they controlled time itself. Moving them outward made the clock run slower. Pushing them inward sped things up. But the adjustments were incredibly sensitive. Moving a weight by just a few millimeters could change the clock's daily rate by several minutes. Finding the perfect position for these weights required obsessive attention to detail that would drive modern engineers to drink. Master Hanuš probably spent months making tiny adjustments, comparing his clock's performance against sundials, water clocks, and astronomical observations. The process was like tuning a guitar by ear, except the instrument was made of iron and brass, and being slightly out of tune meant the entire city would be late for everything. The winding schedules became a crucial part of the clock's daily operation that nobody had really thought through during the design phase. Someone had to climb that tower every day or two to pull the weights back up to their starting positions. This wasn't just a matter of physical strength. The timing of the winding was critical to maintaining accurate timekeeping. Wind too early, and you might disrupt the mechanism's rhythm. Wait too long, and the clock would simply stop. Town officials probably drew straws to see who got stuck with winding duty. Imagine being the poor soul responsible for keeping Prague's most important timepiece running, knowing that if you forgot or couldn't make the climb due to weather or illness, the entire city's schedule would be thrown into chaos. No pressure at all, right? Just the weight of civic responsibility resting on your ability to haul heavy stones up a tower shaft twice a week. The maintenance cycle that kept this mechanical marvel alive for centuries was probably figured out through trial and error over many years. Cleaning meant completely disassembling the mechanism periodically to remove accumulated dirt, dust, and the inevitable corrosion that attacked iron components in the damp climate of medieval Prague. This wasn't a simple weekend project. It probably took weeks to properly clean and inspect every gear, every pivot, every bearing surface. Oiling was another critical maintenance task that required knowledge that came only through experience. Too little oil, and the mechanism would wear out quickly from metal grinding against metal. Too much oil, and dust would stick to everything, creating an abrasive paste that was worse than no lubrication at all. Master Hanuš had to figure out exactly which components needed oil, how much to apply, and how often to reapply it. Restringing the weight systems was probably a monthly or weekly chore that kept everyone on their toes. Hemp rope was the best material available, but it stretched and weakened over time, especially when supporting heavy loads in all kinds of weather. A broken weight cord could damage the entire mechanism if the weight fell uncontrolled, so regular inspection and replacement were essential for the clock's survival. The mathematical precision required for all these maintenance tasks was staggering when you consider that Master Hanuš had to figure everything out from scratch. Modern clockmakers have centuries of accumulated knowledge and standardized procedures to guide their work. But the Prague clock was literally the first of its kind. A prototype that had to establish its own maintenance traditions through years of careful observation and adjustment. The energy transformation that made the whole system work was pure mechanical genius disguised as simple engineering. A falling weight provided steady downward force, but that force had to be converted into the precise, regular impulses that kept time accurately. The gear train acted like a mechanical transmission, stepping down the rotation speed while stepping up the available torque to drive all those complex astronomical displays. The escapement was where the magic really happened, transforming steady rotational motion into the regular back-and-forth oscillation that created timekeeping. The Virgin foliot system was like a mechanical heartbeat, providing the steady rhythm that divided the continuous flow of time into measurable units. Each tick represented a precise fraction of a day, calculated and calibrated to astronomical accuracy. The gear ratios that drove the various displays were mathematical poetry, expressed in brass and iron. The day wheel completed one revolution every 24 hours, driven by the hour hand through a simple 1.1 ratio. But the month wheel required a 30.1 reduction to complete one turn per month, while the zodiac wheel needed a 365.1 reduction to track the sun's annual journey through the constellations. These ratios weren't just theoretical calculations. They had to be achieved using actual gears with specific numbers of teeth. Creating a 365.1 reduction with medieval gears meant using multiple stages of reduction, each stage introducing potential sources of error and mechanical complexity. The compound gear trains that achieved these ratios were masterpieces of mathematical engineering that would impress modern designers. The separation of going versus striking trains was another stroke of mechanical genius that solved problems most people wouldn't even think about. The timekeeping mechanism needed to run continuously and smoothly, maintaining steady accuracy regardless of external disturbances. But the striking mechanism operated in sudden bursts, requiring significant power to ring heavy bells while potentially disrupting the delicate timing of the main mechanism. By using separate power sources and independent gear trains, Master Hanuš ensured that the hourly striking wouldn't interfere with accurate timekeeping. The striking train could use its own weight and gear system, optimized for delivering powerful impulses to the bell-ringing mechanism. Meanwhile, the going train could focus entirely on maintaining steady, accurate time without having to deal with the shock loads created by bell striking. This separation also made maintenance much easier, since problems with the striking system wouldn't disable the basic timekeeping function. If the bell mechanism jammed or broke, the clock would continue keeping accurate time, even though it couldn't announce the hours audibly. In a medieval city, where accurate timekeeping was becoming increasingly important for commerce and daily life, this redundancy was crucial for the clock's acceptance and long-term success. The automation systems that brought the wooden figures to life were perhaps the most impressive demonstration of Master Hanuš's mechanical imagination. These weren't just decorative afterthoughts. They served important social and practical functions in medieval society. The moving figures provided visual proof that the great machine was working properly, even for people who couldn't read the numerical displays or interpret the astronomical information. The pinned barrel system that powered these automata was like programming a computer using physical hardware instead of software. Each pin had to be placed at exactly the right position to operate the correct lever at the precise moment when its corresponding figure needed to move. The timing had to coordinate perfectly with the striking sequence, creating a synchronized mechanical performance that played out automatically, hour after hour, year after year. The forces and leverage ratios needed to operate the automata had to be calculated as carefully as any other part of the mechanism. Each wooden figure required a specific amount of force applied for a precise duration to create convincing movement. Too little force, and the figures would barely twitch. Too much force, and the delicate wooden carvings might break under the mechanical stress. So there you have it, the incredible story of how three medieval craftsmen, armed with nothing but hammers, files, and pure determination, built what was essentially a mechanical computer that could predict the movements of celestial bodies centuries into the future. Master Hanuš and his team didn't just create a clock, they built a machine that transformed the abstract concept of time into something tangible, visible, and utterly reliable for an entire city. Think about what they accomplished with the tools and knowledge available in 1410. No electricity, no precision measuring instruments, no computer-aided design software, just skilled hands, mathematical genius, and the kind of obsessive attention to detail that would make modern engineers weep with envy. They took the steady pull of a falling stone and turned it into astronomical accuracy that lasted for centuries. The Prague Astronomical Clock stands today as proof that human ingenuity knows no bounds when passion meets purpose. Every gear tooth cut by hand, every weight adjustment made by candlelight, every mathematical calculation worked out with medieval arithmetic, all of it came together to create something that still draws crowds of amazed visitors more than 600 years later. The next time you glance at your smartphone to check the time, remember, Master Hanuš and his apprentices working by firelight in their tiny workshop, creating mechanical magic that would outlast empires and inspire generations of clockmakers who followed in their footsteps.